Okay, this is the second hour here on Wednesday, chapter 22, part 2. Don't forget, you got a couple days for homework to get going there, but remember, test 2 is lurking out there. This is the last chapter that's coupled together. So we got carboxylic acids into 2 chapters, 20 and 21, on carbonyl compounds, the additions, the reductions, the Grignards, as well as the enamines, imines, and all that fun stuff in 21. And now 22, we're doing the derivatives of carboxylic acids with the leaving group on the side. So let's finish our comparison here on the sideboard, looking at the different derivatives here reacting in neutral water. So all of these are comparing water. We did anhydrides the last hour, and that reaction's done in minutes, very quickly, going to the carboxylic acid. In this case, it's 2 carboxylic acids, symmetric in the case of acetic anhydride. Remember, we said there is resonance here, but look, this lone pair can also resonate over here. And there's only one lone pair in a p atomic orbital. So it's kind of splitting time between the two, okay? And then we've got the what? The strong polar covalent bond there being polarized toward oxygen. So very reactive molecule, because part of the time this resonance is over here, which is going to make the nucleophile attack more readily there. So now esters. We don't have the second carbonyl here. We've got the alkoxy part. Much faster rate constant now, and this reaction's done in days, okay? Well, I'm sorry, slower. It's a lower number. It's higher than the amide. That's what I was thinking about here in a second, but let's see. So we don't have the X resonance here. It is resonating toward here, which is going to lower its reactivity compared, of course, to the acid chlorides. So resonance is slowing it down, but inductive effects is speeding up the acyl transfer now. Let's compare this to amides there. And this isn't blocking on the camera too much, is it there? You can still see this, okay. Okay, we're good there. So amides, have the lone pair also there. It's less electronegative than oxygen, so this lone pair is even more available, right, for resonance here. And it's set up perfectly for that resonance. And that could really lower the bond order there. So let's see what that does to that carbonyl bond order. And it increases the bond order on the nitrogen. So this resonance effect here, double-headed arrow, is very important for amides compared to esters. Why? Less electronegative, 2.8 on the Pauling scale as opposed to 3.5. So this lone pair is more available, okay, which increases the bond order here and lowers the bond order there. We see that in the IR as well, spectroscopy, and we see it in the NMR. These two methyl groups are not the same at room temperature. This one is cis to that oxygen, this one is trans. These have different shifts. Now you don't need to worry about which one's which further downfield or whatever, but recognize that this extenuated or accentuated resonance effect due to amides, increasing the bond order here, lowering it here, makes it less reactive. Why? Because there's more electron density on this carbon now, okay? So it's less available for the nucleophile to come in there. Yeah, it can. If we have just neutral water, though, it takes years for the reaction to go. If we add acid or base here and heat it up, we can get this reaction to go faster. But on its own here, an amide bond will not react with water very quickly and do the hydrolysis reaction. The two products would be what? The methylamine and the carboxylic acid. Here, what are your products? Carboxylic acid and the alcohol, okay, whatever that alcohol is. So different type of products. Well, actually, let's modify this one. Your two products, if you have this in the presence of an amine, the amine will actually deprotonate your carboxylic, which actually points out an important thing coming up that we'll see later on. So anyway, different rates due to the different structural aspects and different products here, okay? So let's go through and begin to do some of these reactions. Let's do the key one here with the acid chloride. The key reaction is with the carboxylic acid, whatever that might be. And we can always convert that with thionyl chloride, SOCl2, to the acid chloride. And from there, if we react that with another carboxylic acid, we can make what? The anhydride. Okay. If we react it with an alcohol, we can what? Form the ester. Okay. If we react it with water, we just go back, of course, to the carboxylic acid. We react it with an amide. And it can be a different amide. It doesn't have to be a secondary amine. It can be primary amine, but it can't be tertiary. And you'll see from the mechanism, you've got to have this hydrogen that can come off as part of the mechanism. And it can't be a quaternary ammonium salt. So it has to be primary or secondary or just ammonia or just NH3, right? And so there you'll get the amide, whatever those are. So the acid chloride's the most reactive one. It has the best leaving group, and that's what we're going to look at there. We already looked at the general mechanism. Let's get to some of the specific reactions. We'll do specific mechanisms for some cases, although the mechanisms, you're going to get bored by this because they're all the same. No, there'll be some nuances, some different effects there, depending on what the reagent is and how we do the reaction. So let's look at this one first, acetyl chloride, and let's react it with acetic acid. Okay. So we'll just stay with the symmetric one here, and we add pyridine here. Now the pyridine is important because HCl is being generated. If we just let that build up, it'll get very acidic and corrosive, and the HCl will actually break down our product. So if we cleanly want the anhydride, which is what we're going for here with the acetic acid, react with acid chloride, the pyridine will function as a base, a mild base, to soak up that proton. You'll see what's going on here. So where's our nucleophile? Well, it's right here. Let's look at the intermediate. It'll look like this: chloride and OH R. Well, it's just a methyl group there. Now, the pyridine could have deprotonated this to begin with. The pK of protonated pyridine is 5. The pK of a carboxylic acid is 5. So that equilibrium is essentially 1. They're both present. You can use either one. If you want to do the deprotonation first, you can. But you can get to this intermediate here, and then you can transfer this proton. This is a very acidic proton then on this adduct here. So if you transfer that, you can get the OH there. Or, and I'm going to show you the other variation, you could have used pyridine to deprotonate here first too. I kind of like looking at this intermediate because then we can bring this down and get the true protonated form of the anhydride product that we're looking at here. So there's chloride coming off, and we've got H here still on there, right? So that will be the protonated form of that. And so pyridine, and like we said, it could deprotonate at a couple different spots along the way. You can use it to deprotonate here. And I like to do it at the end because you see then what the structure of the byproduct is. It's not HCl. Chloride's happy on its own. That was our leaving group right here, right? Leaving group did its thing. That's why they're the most reactive one. There's no resonance overlap here, and it's just a strong inductive withdrawing group there. Pyridine then takes the proton off. Here's the product we want, right? The anhydride. And that's the key thing we're trying to get to. What's the byproduct? Well, pyridinium chloride. So that has the proton on it. The pKa of that, like I said, is 5, which you see is close to the pKa of the carboxylic acid. So we could have deprotonated some of that there and made it a little more nucleophilic, right? The anionic form of that. But that's okay. And so the chloride's just here. That's a salt. Actually, if you cool this solution down, this will precipitate out of solution, which is nice. You can then filter that salt, and then you've just got the pure anhydride, not being bothered by an HCl byproduct. I like to point out these practical aspects if you leave out the pyridine on a quiz or a test and just show the carboxylic acid with the acid chloride, we'll still give you full credit, okay? It still forms, but in a practical sense, we usually add a mild base to these type of reactions. All right, let's look at the next one here, which is acid chloride, and we're going to form an ester now. So we formed anhydrides first. That's the next most reactive derivative. Now let's form the next more stable one, and that's going to be an ester. So we're going to react the acid chloride with an alcohol, ethyl alcohol and benzoyl chloride. And again, we're going to have pyridine in there. Now you can see pyridine is not a strong enough base to take this proton off. So the alcohol is nucleophilic on its own to go to the tetrahedral intermediate. So we'll have O minus chloride, and we still have that hydrogen on there. So I'm being very detailed about the mechanisms here. Your book is a little skimpy, I'd say, on these mechanisms. I like to show you the whole story. You don't need to be as complete on a quiz or a test. Well, on the test, we can ask you about mechanisms, of course. We can ask you about different aspects of it, or why is this reagent in there, or what's the key intermediate, whatever. So we can still do that on a multiple choice thing, but on the quizzes too, you'll see some detailed mechanisms you've got to be aware of. So at this point, what can we do? Well, we can have pyridine take this off, or we can have the O minus come and grab that proton off, okay? It doesn't matter, whichever one you want to do. Let's have pyridine act right here this time, take that proton off, okay? And what do we have? We still have the O minus up there. And now we have the neutral alkoxy group here. And then what? Pair of electrons can come down, chloride can come back off. And what do we get? Yes, we get the ethyl benzoate ester. Okay, ethyl benzoate. And our chlorides there, pyridinium chloride is still there. That same salt that we talked about before. There's where the leaving group comes off. So yeah, it's the same mechanism exactly, right? Pyridine is often used. Triethylamine could be used also there. The tertiary amine. Pyridine's nice. Like I said, that's a salt that will often precipitate out of the solution. Okay, let's look at the next one, which will be the amides. We could do an analogous thing for thioesters here. I'm going to skip over that. Let's go to the amide formation. So if we have dimethylamine, so this is the nitrogen with a hydrogen and two methyl groups on it. And get this, now we can use sodium hydroxide, a cheaper base, much cheaper than pyridine. Pyridine has an odor. Industrially, on large scale, we try to avoid pyridine at all costs. In the lab, it works fine. But industrially, they like to use these cheap bases. You can use carbonate to soak up the HCl in the previous reactions we looked at. Pyridine, I like to point that out, the pKa difference. Here, you can use sodium hydroxide as your base, okay? So we're going to form an amide here. How's this reaction going to work? Let's go ahead and do our tetrahedral intermediate. It'll look like this, isopropyl, O minus, Cl, nitrogen with all three of those things on it. That'll be an ammonium cation, right? Make sure you know this formal charge. Why is that initially a cation? Well, it brought along this hydrogen. Okay, what can hydroxide do now? Well, it can deprotonate, right? So we've got OH minus, take the proton off. And what's our byproduct here then? Right, water. So there's our nitrogen now with the lone pair on it, back to being neutral. This is still the minus part. Let's bring the pair of electrons down here. Leaving group, just like before. And so what's our product? Yeah, it's the amide. In this case, it's the NN dimethylamide. Now, I like to point out, why can we get away with this base? This base is also a good nucleophile, right? How come we didn't have this go in here and function as the base? Then we wouldn't have gotten an amide product, right? We would have gotten a carboxylic acid, okay? Or the carboxylate with the excess hydroxide. So what does this mean? If we can get away with using sodium hydroxide in the presence of an amine, and the amine wins out, it's the better nucleophile, Why? Well, because oxygen, Pauling scale 3.5, even though it's charged, okay, it's not as good as nucleophile as this. This lone pair is on a less electronegative atom, 2.8, and even though it's neutral, amines are very good nucleophiles. They can do SN2, they can do all those reactions we learned in 351 in that case. The amine cannot be a tertiary amine. This is a secondary amine. We could do the same thing for a primary amine, or just ammonia would do the same reaction. But what about a tertiary amine? 3 alkyl groups? What would happen there? No reaction. Well, it does actually react, but it reverses, gives a different product. So let's see, with the tertiary amine, it would give this. O minus Cl, nitrogen with 3 alkyl groups on. Well, 4, counting the tetrahedral intermediate carbon, right? So what can occur here? Well, hydroxide or any base can't take a proton off now. You'd have to break a carbon-nitrogen bond, which is much stronger than simple deprotonation. So this will just reverse back off, or it will kick off the chloride. Chloride's a better leaving group, and it'll give this. Now these acyl quaternary salts are very susceptible to water. And we've got water in here from the sodium hydroxide actually, and then this will just pop that back off. We need to just have 2 alkyl groups at the most to have a stable amide. It can't be a tertiary amine to give that. It would be reversible. So there are some limitations here we need to be aware of. Okay, acid chlorides. Just to review quickly, we've reduced those with LAH to primary alcohols. We can react those with excess Grignard reagents to go to tertiary alcohols. And cuprates will actually add here. If we have diethyl cuprate and an acid chloride, don't forget that reaction. That will give us a ketone product. So acid chlorides are very, very versatile, we can say there. All right, let's look at the reactions of anhydrides now. So those are the reactions of acid chlorides. So we're going to kind of go through all the derivatives sequentially here. I'm not going to show you every possible combination, but you need to think about that, the hierarchy of the reactivity. From the acid chlorides, you can make all the derivatives, okay? So let's see here, anhydrides. Let's take acetic anhydride and react it with ethanol, and we're going to use a drop of H2SO4. Wow, now we're switching over to an acid catalyst. Now, actually, if you leave out the acid catalyst, it'll still go, but this reaction with alcohols is similar to water, so it's a very fast reaction anyway. The more hindered anhydrides will require a little bit more acid to get them to go. So we'll see part of the mechanism here, how this might relate. So if you do have a strong acid in there, you can actually protonate your anhydride. So the intermediate would look like that, okay? Well, what does that do to the reactivity? And again, if you had a hindered group here, or a hindered alcohol, the acid catalysis would really help you out here. This makes this what? More reactive. It's polarizing these electrons more up here and making this more electropositive. So the nucleophile can attack there better. So what do we get? And you see our tetrahedral intermediate now involves the neutral alcohol at that point. And we've got the ethoxyonium ion down there for our tetrahedral intermediate. So you see how these are all similar? But a little bit different now. We have instead of chloride as a leaving group, we have this here, okay? So what can we do to make this a better leaving group? Well, let's transfer that proton. And I'm doing it in an intramolecular sense. And Aaron and others might ask, well, can we take that off and then put it back over here? Yes. Okay, you can always do it stepwise. This is a good leaving group on its own already, but let's use the acid available catalytically to transfer it over there and see how that affects the leaving group ability. So we'd have O carbonyl protonated, yeah, and O ethyl now is neutral, okay? So we just transferred that proton. Now let's go ahead and push the electrons back down here, and what? Push them over there to give the neutral acetic acid as a leaving group. We don't have to invoke acetate coming off. So here's our ethyl group, and then what do we have here? We have acetic acid as our byproduct. Okay, so we just broke that bond right here. You see we're already going to the carbonyl of, where are we going here? We're going to the ester, right? So we can take that off. We can use, we got a little bit of water in there. And of course, a lot of times we have the solvent as the alcohol or excess alcohol. Even if we don't, we could use water here to take that proton off. And that will give us what? The ester product, okay? And this would regenerate our catalyst, our acid, okay? So the acid's just in there to help out a little bit. Acid catalysis we'll see very important for the formation of esters from carboxylic acids and alcohols. But this is a reactive of an anhydride with an alcohol to make the more stable ester, okay? And these can be formed in high yields here. All right, let's look at the reaction here with amines and see what we need to know there. Let's take acetic anhydride with benzylamine. So here's benzylamine, more complicated amine here. And let's see. Well, we don't really need to add acid catalysis here. This is a very good nucleophile, better than an alcohol. Let's just go ahead and attack directly here. And we're forming a more stable product, the amide product. So don't worry about my little variations here, the reagents and the substrates. First two we added pyridine, then we added hydroxide. Could have used other bases there, but they're all involved the same thing, nucleophilic attack, tetrahedral intermediate, and then leaving group. And with anhydrides, the leaving group is going to be the carboxylate, okay? So if we attack here, what do we get? O minus. We got O, the acetate part, and then we've got the amine here, which will, have the benzene there and the two hydrogens on it. So what can we do at that point? Well, we can transfer a proton here off of the ammonium. So we have OH, acetate, and the neutral amine, which will become the amide, of course. Now let's have this take off, and let's kick off acetate, okay? So we'll have the protonated form of the amide, benzyl amide, and then acetate. And we could abbreviate that as OAC minus, okay? Those are the same thing. We often abbreviate acetic acid as AC, acyl group, acetyl group. And so that can function as the base, you see, and that will give us the amide product. And it's a benzyl amide, so I'll use the correct designation for that benzyl group, which is a methylphenyl group. So this is N-benzyl acid amide, formed from the acetic anhydride and benzylamine, okay? Let's look at a cyclic version of our anhydride. And these cyclic anhydrides can be a little bit tricky. We have a cyclic anhydride. We've got this here, and then 1, 2, 3, 4 extra carbons there. So 5, 6, so it's 7, 8. It's an 8-membered ring. Well, let me make sure. 1, 2, 4, 5, 6, 7. 7-membered ring. Okay. And it's got 6 carbons here. And let's react it with methylamine. Okay. Well, let's think about this. So here's our nucleophile. Let's go through the mechanism. Just briefly like this. So tetrahedral intermediate, and then let's just bring this down and have this come back off and transfer the proton there. What's our product going to be? Well, it's going to be this N-methyl amide there on one of them there. But let's see, what about the other one? The other carbonyl will be carboxylic acid. Now, why is that? Well, you've got one side being the electrophile, and this other side is just the leaving group, okay? There is a way to put this other one on here. You'd have to adjust the conditions, though. This is room temperature, okay? with just one equivalent here, adding here. Carboxylic acids are far less reactive than anhydrides. And it's only at the beginning you have the anhydride electrophile, right? You don't have an anhydride electrophile now to do the second substitution easily. You'll get the monoamide carboxylic acid product from a cyclic anhydride. So yeah, that's a little bit tricky thing, but it follows out of the mechanism. Now, speaking about cyclic anhydrides, let's look at this one. These do have names. I'm not going to make you know that, but this comes from a 4-carbon dicarboxylic acid. So this is succinic anhydride. It comes from taking succinic acid and actually just heating it up. Delta is the sign for heat. Now, how might that work? Well, look at what's being eliminated from the molecule. You're removing water. So the heat can do that. And then mechanistically, I'm not going to go through the whole thing. You can. How would this work? Well, a pair of electrons here can go in, tetrahedral intermediate, come back down. You have hydroxide as a leaving group. Yeah. Hydroxide would then deprotonate over here. And that's okay. That's what the heat's for. But you see these 5-membered ones and the 6-membered ones are okay as well. You can easily form these cyclic anhydrides, okay? Similar to this one we had up here, which was what, 6 carbons. You'll see, you can have aromatic ones from di acids. This has a great name. This is phthalic acid, PHTH in the name there. And if we heat that up, let's see, I got them in the reverse order there. We can make phthalic anhydride. And these ones that, again, have the 5 and 6-membered rings are favored that way. With the loss of water, can make what's called phthalic anhydride. You can take this also with nitrogen from ammonia. If you heat this up with ammonia, for example, what happens here? Well, here you've got a nucleophile here, and you'll form the amide there, and because this is in a ring, and you have to heat it up to get it to go. But you can draw the mechanism for this too. You can make the Imid, it's called. Okay, there's another functional group for you. An imid is actually a diacylamine. And don't worry about that, but there's a bunch of these, and you may, think about this one. What did we call this reagent? NBS, N-bromosuccinimide. Here's succinic anhydride. And you see, if we took succinic anhydride with ammonia, we'd get the succinimide. And then, yeah, you have to treat it with an electrophilic bromine source in order to get the N-bromo on there. But you see the imide structure that we talked about there in the aromatic one. But be aware of those cyclic ones and how those mechanisms may form. All right, let's go on to esters. And esters are going to give us a lot of important products. We're going to spend quite a bit of time on esters, probably going into Friday's class time and reviewing a lot. Esters are very versatile. They're kind of in between in stability. They are reactive, but they're stable enough to water to be around for a given amount of time. So fat storage is based on the acyl triglycerides, the triester, the polyester material. But proteins, peptides, are not based on polyesters. Those would not be stable enough long term. The amide is the most stable derivative. But let's look at esterification. Esterification developed by Emil Fischer, and he showed that you could take a carboxylic acid, which is a nasty, sharp-smelling material, and this is the magic, I think, of chemistry. Take this with an alcohol, ethanol, and this is often the solvent for Fischer esterification. So ethanol or methanol or other simple alcohol here, and then acid catalysis. So either HCl or H2SO4 catalysis here, and you can get ester to form. Okay. So yeah, how does this work? The mechanism was somewhat of a mystery for a long time. I'll give you some key ideas here as to how the mechanism's actually going to work. If you have heavy isotope oxygen labeled ethanol, and this is the heavier isotope, the naturally occurring isotope, the most abundant one is O16. So O18 isotope has what? 2 extra neutrons in the nuclei. And that can be traced by mass spec and some other simpler techniques. You can see how the molecular weight goes up or wherever. Where does this O18 end up in the product here? Well, we have a byproduct here, which is going to be water. Does the O18 end up here in the water, or here, or here? Okay. Well, it ends up right here. Okay. And you can trace that. It'll end up in the alkoxy group. So our mechanism has to account for that. There's a couple different ways to draw the mechanism, but I'm going to show you the one that's accepted, that's consistent with all the available data we have from how the reaction has been conducted and from theory. Okay, so you can model all these intermediates and show that this is the low energy pathway that we're going to do here. Okay, so if we have HCl and alcohol here, we're going to protonate the alcohol, okay? And that's, you know, pKa of what? HCl, that's pK of -7. pK of hydronium ions -2. So that's favorable to go to the less reactive acid, right? It's an inverse scale. The lower the pKa here, the more reactive the acid is. So -7 for HCl. So yeah, you can protonate it, especially if that's a solvent, you have excess there. Okay, well, what else can we do with this proton? You can also transfer it to the acetic acid. Now, I've used acetic acid as what? A base. Can acetic acid function as a base? It sure can. If it's in the presence of a stronger acid, that stronger acid overrides the ability of the carboxylic acid to donate a proton. And you see carboxylic acid just accepted a proton. This was our base. This was our acid, okay? And it's not very favorable. The pKa of this itself is also -5, I think, or so. So it's not forming much. This is reversible. So I should have double-headed arrows here. I may leave them off, but recognize that this is fully reversible. Why is this going to form a high yield of this product? Because this is excess. And oftentimes we heat this up and drive off the water. So again, Le Chatelier's principle, even though some of these steps are not favorable, we can do this. And in fact, you know, mechanistically, we're just trading one carbon-oxygen bond for another, right? And we're transferring a proton. So if you look at the bond dissociation energies, this is a wash. It's about the same. What really affects the equilibrium here is excess alcohol and heat driving off the water, okay? Well, mechanistically, let's see how we get there. So what do we got? We've got ethanol. Let's go ahead and attack there. We've got this now, and that's kind of a funny looking thing, isn't it? It's carbon with 3 oxygens on it. It looks like the CHEM diol. We talked about the hydrates there, but it's got the alkoxy group on it. And again, it's the attack. Here's our nucleophile. There's our electrophile. So it's really the same thing. The only thing we got to account for is what, driving off the water and getting to this ester product. So how are we going to do that? Let's transfer one of these OH groups is going to grab that proton off there. And that's going to then look like what? OH with the 2 there, and now the alkoxy is neutral. And again, all these are reversible. Sorry, you caught me. Yeah. Aaron didn't even need to say anything then. I remembered to draw the... Okay, so we get this. And why are we transferring a proton here? Because we got to get to water, right? So let's go ahead and break that bond. And this bond's going to be weakened now because of that, right? So it went on, the alcohol had the proton there. Then we transfer the proton over here so we can get water coming off. And if we pull water off there, right, what's this right here? It's a cation, okay? And notice it's resonance stabilized here and here, okay? And it's what? It's tertiary. So yeah, that's a good carbocation due to the resonance donation, not due to the inductive withdrawal. Remember, through the sigma bonds, these are polar covalent bonds the opposite way. But by resonance, this is helping to stabilize that. And that's what we need to get to. We need to get to the carbonyl of the ester, right? So let's see, if we do that, bring that down resonance-wise, we get to this. We'll still have the proton on there. We've got water here. So what can occur now? Well, we can use water to take this off. Do we have any other bases in there? We've got more alcohol. We've got a couple different bases we can use. We don't have much water at first. This is anhydrous to begin with, right? We don't want water in there because that would favor the reverse reaction, the hydrolysis of the ester. We're favoring formation of the ester using excess of the alcohol. So because we still have excess alcohol, let's use that as our base there. And you see that gives us our product, okay? And it regenerates the acid catalyst, which is this guy, right? So we regenerate our acid catalyst, which is really the protonated form of the alcohol. Can we follow where our O18 label ended up? Is this mechanism we've just drawn consistent with the result that the O18 heavy atom should end up there if our alcohol is labeled such as that? Let's see, that would be here, right? Or here, right? Okay, there it is, right there. It'd be right there. Yep. And you see it doesn't exchange with these. This stays with the ethyl group on it. Yep. Okay, that would be consistent. Yep, there it is still there. And there it is here where it ends up in the product. So yeah, that tracer was actually used to confirm the thinking about this, but we could draw this mechanism in a couple different ways that would exchange that in a couple different spots. I'm not going to go through those alternative mechanisms. Let's just stick with the one that's known there. But this generates obviously the product, the byproduct, and it accounts for the reversibility and how we might change that with excess alcohol and removing the water there. Okay, so questions on that? Yeah, usually there's a few questions on that point, and I'll pause for a minute or maybe erase the board and see if you can, in groups, come up with this mechanism again on your own. We can't do that, but you can pause your video and look away and see if you can come up with that mechanism now. If you can't, practice it and make sure you can see how that's going to work. All right, let's look at an intramolecular esterification. Still got some time here. Let's see. We can have a hydroxy carboxylic acid. And we have an alcohol here. Let's just add a little bit of catalytic acid here. Maybe heat this up. What's going to be the product here? We're not adding any alcohol. The alcohol is already in the product, right? And mechanistically, you can think about how this might work. Sulfuric acid could protonate the carboxylate or other places. But once it protonates there, we can have this attack here, right? And then we can what? Eliminate water. Water will be a byproduct. And what's our product in this case? Yeah, it's the lactone. And which lactone is it? Let's see, 1, 2, 3, 4 carbons. 2, 3, 4. Yeah, alpha, beta. This is the gamma lactone product. Okay. And oftentimes these happen spontaneously. You don't really have to have catalyst in there. Catalyst in there allows you to do it at room temperature. You can heat it up actually without the catalyst, and this will lose the water, kind of like the cyclic anhydrides we just did. So these lactones can be favorable that way. If we add water to this, you can go back and open it up to the hydroxy acid. So you can kind of see how that would work too, right? Attacking here, transferring the proton and opening up. And again, depending on the conditions. All right, the last topic for today is going to be esterification under neutral conditions. And the neutral conditions are going to involve this reagent called DCC, dicyclohexylcarbodiimide. And this will allow us to do an esterification. I'll show you the esterification from benzoic acid using ethanol. This will be one equivalent to one equivalent, not the solvent, okay? And this is the other great thing about DCC now. DCC, or carbodiimide, we'll draw out the structure in a second. This will allow us to form the ester in high yield at 1-to-1 stoichiometry. Now the DCC is kind of an expensive reagent. On large scale, it would be a significant cost. Ethanol is very cheap, so most ethyl and methyl esters are made by the Fischer esterification with catalytic acid. But DCC, especially if you have a precious alcohol now, an expensive alcohol, and it works as secondary alcohols as well. Tertiary alcohols are very slow. but it can be a primary alcohol or a secondary alcohol and be quite complicated here. And at 1-to-1 stoichiometry of DCC, you get the ester product. And notice there's no added acid here. It's neutral conditions, okay? So if you have a molecule that's sensitive to acid, you want to use DCC. And what's DCC? Well, it's a carbodiimide. And it's got 2 cyclohexyl groups on it there. And yeah, this is the carbodiimide. So it's dicyclohexyl and carbodiimide. Diimide, well, we just told you what an imide is. Imide is a diacylamine, but a diimide is actually a carbon with 2 imines on it. That's where the term comes from. Carbon with 2 imines, carbodiimide. And the cyclohexyls are just on the side here. The byproduct, and this will be part of the driving force for the reaction, ends up like this. The 2 cyclohexyl groups on there, I'll just say R. 2 hydrogens are, this is actually called urea. And if these R groups were hydrogens, that's actually the waste product of excess nitrogen in higher animals. Urea, you've probably heard of urea in urine, whatever. This isn't a urea from urine. This will have dicyclohexyl groups here. But you see the elements of water are there, 2 hydrogens and this oxygen here. So that will be where the water ends up. Carbodiimide actually sequesters water, and that's part of the driving force for this reaction and lets you to do it at 1-to-1 stoichiometry. So let's see if we can do some of the mechanism here. Briefly, we've got enough time, I think. Yeah, okay. We can do it, I think. Let's see. So first step, we're going to protonate the imide, and I'm just going to abbreviate the cyclohexyl groups on there as R groups, okay? So we'll initially have this. So yeah, that's from benzoic acid, and we just used the lone pair of the carbodiimide to grab the proton off there, okay? And now we can attack here and push the electrons over there. And you see we've got then the nitrogen and our R group right there. So we've got the carboxylate right there, okay? So what we've done is we've added the carboxylate anion, which is a good nucleophile, it's charged, and this is very electrophilic carbon, right? With this plus charge here, we can flow the electrons over there and get this neutral intermediate right there. Looks like that. Now our alcohol, okay, which is a relatively weak nucleophile, feels this activation of the carbonyl at that point. Okay, this isn't a carboxylic acid anymore. It has this urea thing. You can kind of see the oxygen's already on the carbon becoming the urea there. Let's go ahead and attack that. This is the slow step in the mechanism, but if you push the electrons that way, you can see the O-ethoxy, and you've got the, oops, oh, let me make sure I've got this right. Okay, oop. O minus, O-ethoxy, and that has the proton on it, and the phenyl group there. And what else is over here? Well, our nitrogen is still got that other cyclohexyl R group on it. Okay, so there's our tetrahedral intermediate. Again, it's a tetrahedral intermediate, O minus right there, okay? And let's see, what are we going to do here? Well, we can bring this pair of electrons down now, and let's push these electrons onto here, okay? We still have this O hydronium here, and sorry, I can't push that board up. Can you see past the, it's okay. All right, I'll draw it a little higher there. Okay, so here's our intermediate leading to the ester, okay? And what does the rest of the reagent look like? Well, it's going to have that CNH with the R group, and this one along with the R, okay? Yeah, complicated mechanisms, right? You can already see the ester, right? We've got the ethoxy group on there. It's got this plus charge. So what can we do with that? Well, let's bring this down, And then let's use this pair of electrons over here to grab that proton. So sorry about the big arrow there, but that is the flow of electrons. That will give us the benzoate product, the ethyl benzoate, okay? And it gives us, let's see, the urea. And this is cyclohexyl here, right? And now this one over here has a hydrogen on it, and that's also the cyclohexyl. So there's our urea byproduct. It's often a solid material. It can be precipitated out or chromatographed apart, which can be kind of a problem. But there's our ester, formed under neutral conditions with one equivalent of DCC, one equivalent of the carboxylic acid, and one equivalent of the alcohol. Now, a lot of times we'll add a little bit of excess of the alcohol, but it's not the solvent in this case. The solvent can be methylene chloride or THF in this case. But the thing is, you can use more complicated alcohols here to get very complicated esters formed in high yield with the byproduct being urea. Why is urea a good byproduct? Because of the resonance stabilization, right? You can see that all over the place. The two lone pairs make urea a very stable form of nitrogen. And there's where your water ends up. You can see where the elements of water came out of this one originally going on there, right? And that becomes our acyl electrophile right there, okay? Because this is a better potential leaving group now. It's not as good as chloride, but it's about as good as an anhydride because once this comes off right here, see it's resonance stabilized, right? So there's a number of things we can look at there. And here's our nucleophile going on. It's the only other thing we have that's nucleophilic at that point. The first thing is right here because the carboxylate's a better nucleophile. The oxygen of the alcohol doesn't add there, the carboxylate does initially. Then it waits around for the weaker nucleophile, the alcohol, to attack there. Tetrahedral intermediate, just like before, we gotta have that come off. And that functions as the base. That will take that proton off. So that becomes the base. And there's our byproduct there. So yeah, we can identify things, the nucleophile, the electrophile, the tetrahedral intermediate, and hopefully it looks similar to the other mechanisms we've covered. So I think we're good there on time. Oh, one more. Sorry. One other way to form esters. Very versatile, right? You can also do this. Let's take our benzoic acid. Let's treat it with sodium carbonate, very cheap base. That will give us sodium benzoate. And then what can we do? Let's say we want to form that same ethyl benzoate. What do I need to add here? Ah, that's a 351 reaction. We just need to add ethyl iodide or ethyl bromide. And what type of reaction is this then? Ah, that's good old SN2. Okay. So yeah, you can form it from this under basic conditions, or the Fischer esterification, or the DCC coupling. And so why are we showing you a bunch of different ways to form esters? It's the versatility. This one's limited to what? Primary type things. Secondary might give some elimination and be slower, okay? And excess of that would be more expensive than a simple alcohol under acidic conditions to do the esterification. Anyway, so keep those three things in mind, work those mechanisms. We'll pick it up next time with a little bit more on esters. We'll get to amides. And then second hour next time, we'll do the sample tests. So be tuned in for that on Friday. So very good. Thank you. We'll see you next time.